So as shown over here, we are having the cantilever beam subjected to the point load at the free end. And because of this particular load W, there is a deflection of the beam. So this is the fixed end of the cantilever beam and this is the free end of the cantilever beam. So from point B dash we have drawn this tangent and this tangent is making an angle of theta. So this is nothing but the slope and the distance B dash is nothing but the deflection of the beam. Now the boundary conditions, as we can see over here, at this particular fixed end there is no slope. So slope is 0 and therefore at x is equal to 0 the slope is 0. Similarly at x is equal to 0 there is no deflection and therefore y is also equal to 0. Now let us consider a section xx at a distance x from the fixed end as shown over here. So if this is x and this total span length is L, then this distance will be equal to L minus x. Now we'll take the moment about this section, that is xx. So we know that the equation for the moment is a second order differential equation. So ei d2y by dx square is equal to moment at section xx. Now on the right hand side of this particular section there is only one load, that is W, and this W multiplied by the perpendicular distance, that is L minus x. So W multiplied by this perpendicular distance L minus x is nothing but the moment, and as it is producing the clockwise moment about this section, we have considered the convention that the clockwise moments they are negative, so it is minus W into L minus x. Now integrate this equation with respect to x. So here it will be ei dy by dx is minus W as it is. Integration of L minus x is L minus x square divided by 2 and again divided by the coefficient of x. Coefficient of x is nothing but minus 1 over here plus some constant of integration, that is c1. Now this minus and this minus sign will get cancelled. So we are having W upon 2 L minus x square plus c1 as our second equation. Now again integrate with respect to x. So it is eiy this W upon 2 as it is, and again the integration of L minus x square, that is nothing but L minus x cube divided by 3 and again divided by the coefficient of this x, that is nothing but minus 1 over here plus c1x plus some constant of integration, that is c2. So this is nothing but minus W upon 2 into 3, that is 6 L minus x cube plus c1x plus c2. So in this way we have obtained these equations, second equation and third equation. Now using this second and third equation and substituting these boundary conditions, we can find out the two unknowns, that is c1 and c2. So if we use the first boundary condition, that is at x is equal to 0, dy by dx is equal to 0, and substitute that in equation 2, then from equation 2 we are having this ei dy by dx is nothing but 0, this W by 2 as it is. In place of x it is 0 plus c1. So this term is 0 and this is WL square by 2 plus c1. So we can say that the value of c1 is minus WL square by 2. Similarly, we can use the second boundary condition, that is this particular boundary condition in equation 3. So at x is equal to 0, deflection y is equal to 0. So ei into 0. So in place of x it is 0. Here also in place of x it is 0. So this is 0. This term is minus WL cube by 6 plus c2. So we can say that c2 is WL cube by 6. Now we have obtained the two values, that is c1 is minus WL square by 2 and c2 is WL cube by 6. So we can substitute these values of c1 and c2 in equation 2 and 3. So from equation 2 we are having ei dy by dx is equal to W by 2 L minus x bracket square plus c1, and value of c1 that we have obtained is minus WL square by 2. So in general we can say that slope is given by this EI term we have transferred on this side, so 1 upon EI, and this W by 2 L minus X bracket square minus WL square by 2 as it is. So this is our first equation which will represent the slope of the curve. Similarly, from equation 3, we are having EIY is equal to minus W by 6 L minus X bracket cube C1. C1 value of C1 is minus WL square by 2 into X as it is, and this C2 is nothing but WL cube by 6. So we can say that the deflection Y is given by 1 upon EI and this term as it is, that is minus W by 6 N minus X bracket cube minus WL square by 2 into X plus WL cube by 6. Now let us consider our first equation, that is the equation of slope, and we know that maximum slope is at free end of the cantilever beam. So at free end the condition is X is equal to N. So put X is equal to N in this particular equation. So in place of X it is N. So this will be 0 because N minus N, that is 0, and 0 into anything, that is 0. So ultimately we can say that maximum slope at the free end is minus WL square by 2I. So this is the equation for the maximum slope in case of the cantilever beam. Similarly, we can consider the second equation to find out the slope, and we also know that the slope is maximum at the free end of the cantilever where X is equal to N. So we can substitute X is equal to N in this particular equation. So this is 1 upon EI minus W by 6. In place of X it is N. Here also in place of X it is N. So this term is 0. So this minus WL L square into L, that is L cube. So it is minus WL cube upon 2 plus WL cube by 6. Taking 6 as the LCM, so here it is minus 3 WL cube plus WL cube divided by 6. So this is minus 2 WL cube by 6, or we can say that the maximum deflection is minus WL cube divided by 3 EI in case of the cantilever beam. So in this way we can find out the maximum slope and maximum deflection in case of the cantilever beam. Thank you very much for watching. Do subscribe to our channel. Thank you very much.